As you settle into the gentle quiet of evening, imagine descending far beneath your feet through layers of soil and rock, deeper than the deepest ocean trenches, beyond where sunlight has ever touched, to a realm where our planet's true power lies sleeping. Here, perhaps 60 miles below the surface, in the slow-moving currents of Earth's mantle, a transformation is beginning that will eventually reshape the surface world above in ways both beautiful and dramatic. Tonight, as you rest in comfort above, the Earth beneath you is engaged in one of nature's most patient and powerful processes. Deep in the mantle, where temperatures reach over 2,000 degrees Fahrenheit and pressures exceed anything we can imagine at the surface, solid rock is beginning its ancient dance of transformation. This is where our journey begins, in the birthplace of magma, where the very bones of our planet slowly surrender their solid form to become something entirely new. The mantle, that vast layer of rock between Earth's core and crust, is not the static, unchanging realm we might picture. Instead, it flows like an incredibly slow river, driven by temperature differences that have persisted for billions of years. Heat from the planet's core below warms the mantle from beneath, while the cooler temperatures near the surface create a gentle but persistent circulation. Imagine honey warming in sunlight, developing slow currents that carry material upward and downward in an endless, patient cycle. As you breathe deeply and let the day's tensions fade, picture these mantle currents moving with the unhurried pace of deep time. A single circulation might take millions of years to complete, carrying solid rock upward toward regions of lower pressure and higher temperatures. This is where the magic begins, where solid becomes liquid not through the addition of heat alone, but through the elegant physics of pressure and temperature working together. The rocks of the mantle are composed primarily of olivine and pyroxene, minerals with names as beautiful as their crystalline structures. These minerals have specific melting points, but here in the deep earth, melting doesn't happen all at once. Instead, it's a gradual process called partial melting, where only certain components of the rock begin to liquefy, while others remain solid. Think of it as nature's own selective process, choosing which elements will join the molten journey ahead. As mantle rock rises in these ancient convection currents, something remarkable occurs. The pressure decreases gradually, and this decrease in pressure, called decompression, is often enough to trigger melting without any increase in temperature. It's as if the rock, having been compressed for eons, finally has space to expand and transform. The first minerals to melt are those rich in silica and alkali elements, creating the earliest drops of what will become magma. This process unfolds with a patience that matches the timescales of our planet itself. The initial melting might begin as tiny pockets of liquid scattered throughout the solid rock matrix, like dewdrops forming on a spider's web in the early morning. These first traces of melt are incredibly important, for they represent the beginning of a chemical journey that will eventually create the diverse array of volcanic rocks we see at Earth's surface. As the partially molten rock continues its upward journey, more melting occurs. The composition of this early magma reflects the chemistry of the mantle itself. Rich in magnesium and iron, relatively low in silica, with a character that geologists call mafic. This is the stuff of basaltic magma, the most common type of magma on Earth and the foundation of the ocean floors that cover most of our planet's surface. The beauty of this process lies not just in its scale, but in its precision. Different minerals melt at different temperatures, creating a natural fractionation process. As partial melting continues, the liquid portion becomes enriched in certain elements, while others remain locked in the still solid minerals. This separation is the beginning of the incredible chemical diversity we see in volcanic rocks around the world. Tonight, as you rest peacefully above, countless tiny pockets of newly formed magma are collecting in the spaces between mantle minerals. These microscopic lakes of molten rock are beginning to migrate, following pathways of least resistance, slowly coalescing with other pockets of melt. The process is so gradual, so patient, that even on geological timescales, it unfolds with deliberate care. The physical properties of this early magma are fascinating to contemplate. At mantle conditions, the newly formed liquid has a density slightly less than the surrounding solid rock, giving it a natural buoyancy, like oil rising through water, but infinitely slower and under unimaginable pressure. These early magma droplets begin their journey toward the surface world above. Temperature plays a crucial role in this deep earth awakening. The mantle's temperature increases gradually with depth, following what geologists call the geothermal gradient. But the melting point of mantle rock also increases with pressure, creating a delicate balance. Only in specific conditions, where the temperature curve crosses the melting curve, can this transformation from solid to liquid occur. These special regions become the birthplaces of magma, scattered throughout the mantle, wherever conditions align perfectly. As the evening settles around you, consider the incredible timescales involved in this process. The rock that is melting tonight in the deep mantle may have been solid for hundreds of millions of years, having formed in previous cycles of melting and cooling, subduction and uplift. Now it begins a new chapter in its geological story, surrendering its crystalline structure to become part of Earth's molten circulatory system. The chemistry of mantle melting is a testament to our planet's sophisticated recycling system. Elements that were once part of ancient ocean floors, carried down into the mantle by subducting tectonic plates, now contribute their unique signatures to new magma. Water, carbon dioxide, and other volatile compounds trapped in minerals during previous geological processes begin to separate and concentrate in the melt, adding complexity to the magma's composition. This deep earth awakening is not a violent process, despite the incredible forces involved. Instead, it unfolds with the measured patience of planetary processes, each step building upon the last, each change preparing for the transformations to come. The newly formed magma pockets are still small, still dispersed throughout the solid rock matrix, but they represent the beginning of a journey that will eventually bring deep earth materials to the surface world. As you prepare for rest tonight, imagine these countless microscopic beginnings occurring far beneath your feet. Each pocket of melt is a potential seed of future volcanic activity, a tiny reservoir of Earth's creative power preparing for the long journey ahead. The solid rock of the mantle continues its ancient convection, carrying both solid and liquid phases upward in a dance that has been ongoing for billions of years. The awakening has begun. Deep in the earth, where darkness is complete and pressure is absolute, the first transformation in our magma's journey is taking place. Solid becomes liquid, stable becomes mobile, and the patient forces of our planet begin once again to reshape the world above. Tomorrow night, we'll follow our magma as it begins to collect and evolve, moving ever closer to its eventual destiny at the surface. But for now, rest peacefully, knowing that far below, the Earth is quietly at work, continuing the endless cycle of creation and renewal that makes our dynamic planet possible. The underground reservoir. Tonight, as gentle breezes stir the air outside your window, our magma continues its slow transformation in the Earth's depths. The tiny pockets of melt we discovered in the deep mantle have begun their patient journey upward, guided by the fundamental forces of buoyancy and pressure. As you settle into the peaceful rhythm of evening, imagine these countless droplets of molten rock beginning to collect in one of nature's most remarkable hidden chambers. A vast underground reservoir of liquid stone. Our journey now takes us to a realm some 20 to 30 miles beneath the surface, where the ascending magma encounters a region of structural weakness in the Earth's crust. Here, in spaces created by ancient fractures and the gradual dissolution of surrounding rocks, our scattered pockets of melt begin to coalesce into something magnificent. A magma chamber, an underground lake of molten rock that may stretch for miles in every direction. The formation of this hidden reservoir is a process of extraordinary patience. Drop by precious drop, magma arrives from the depths below, each addition representing thousands of years of journey through the solid rock above. As the chamber slowly fills, it becomes a laboratory where Earth conducts some of its most elegant chemical experiments, transforming simple mantle-derived magma into the diverse array of compositions that will eventually create the rich variety of volcanic rocks we see at the surface. Picture this underground chamber as a vast cavern filled not with air or water, but with rock so hot it flows like honey. The walls of this chamber are the solid rocks of the crust, gradually heated by their molten neighbor until they glow with their own radiant warmth. At temperatures exceeding 2000 degrees Fahrenheit, the boundary between liquid and solid becomes a dynamic, ever-changing frontier where the chamber slowly grows, dissolving its own walls and incorporating new material into its molten heart. As you breathe deeply and let the tranquility of evening wash over you, contemplate the remarkable processes unfolding in this hidden realm. The magma in our chamber is not static. It flows in slow, majestic currents, driven by temperature differences and chemical gradients. Warmer magma, continuously arriving from below, rises toward the chamber's roof, while cooler magma near the walls descends in a gentle circulation that has continued for thousands of years. This circulation is crucial to the chamber's evolution, for it creates one of geology's most beautiful processes, fractional crystallization. As the magma cools slightly near the chamber walls, certain minerals begin to form. Not the chaotic solidification of rapid cooling, but the ordered, patient growth of perfect crystals. These early forming minerals have a profound effect on the magma's composition, for as they crystallize and settle or float within the chamber, they remove specific elements from the liquid, leaving behind a melt with an entirely different character. The first minerals to form in our cooling magma are those rich in magnesium and iron, olivine crystals that shine like tiny green jewels in the molten bath, and pyroxene crystals with their perfect geometric forms. These dense minerals tend to sink through the less dense liquid, accumulating in layers on the chamber floor, like snow settling in a winter landscape, but snow made of crystalline rock and accumulating over millennia. As these early crystals remove magnesium and iron from the magma, the remaining liquid becomes progressively enriched in silica, sodium, and potassium. This is how our originally simple basaltic magma begins its transformation into more evolved compositions. Andesitic magmas, with their intermediate character, or even rhyolitic magmas, rich in silica and capable of explosive eruptions. Each stage of this evolution reflects thousands of years of patient crystallization and chemical separation. The chamber walls themselves become active participants in this chemical dance. The intense heat of the magma gradually melts the surrounding crustal rocks, incorporating their unique chemical signatures into the mix. If our chamber formed in granite-rich continental crust, the assimilation of these silica-rich rocks will drive the magma toward increasingly evolved compositions. If the chamber lies beneath oceanic crust, the incorporated material will be more mafic, preserving more of the magma's original mantle character. Tonight, as you rest comfortably in the surface world above, our magma chamber continues its slow chemical cooking. Volatile compounds, water vapor, carbon dioxide, sulfur dioxide, gradually concentrate in the melt as crystallization removes the major elements. These gases, invisible but incredibly important, dissolve in the magma like carbon dioxide in a soft drink, waiting for the right conditions to come out of solution and drive future volcanic activity. The timescales of chamber evolution are both humbling and magnificent. A single large chamber may persist for hundreds of thousands of years, slowly evolving, gradually changing its composition through countless cycles of heating and cooling, crystallization and remelting. Some chambers may never erupt, eventually cooling completely to form large bodies of intrusive igneous rock, plutons that will only see daylight millions of years later after erosion strips away the rocks above. But our chamber is destined for a different fate. As it continues to evolve, several processes work together to prepare it for its eventual journey to the surface. The continuous addition of fresh magma from below maintains the chamber's thermal vigor and provides the volume necessary for future eruption. The accumulation of volatile compounds increases the magma's potential energy, like a champagne bottle building pressure before the cork is popped. The chamber's roof, that ceiling of solid rock separating molten stone from the world above, experiences constant stress from the hot, buoyant magma below. Over time, this thermal and mechanical stress creates networks of fractures, pathways that will eventually provide escape routes for our ascending magma. But these developments unfold so gradually that even on geological timescales, they represent the slow breathing of our patient Earth. As evening deepens around you, consider the incredible diversity being created in chambers like ours around the world. Some chambers, beneath oceanic spreading centers, produce the steady supply of basaltic magma that creates new ocean floor. Others, beneath continental margins, evolve toward explosive, silica-rich compositions that will eventually build towering stratovolcanoes. Still others, beneath hotspot volcanoes like those in Hawaii, maintain more primitive compositions but achieve enormous volumes, preparing to build island chains that will persist for millions of years. The beauty of magma chamber processes extends beyond their chemistry to their physics. The way heat moves through the molten rock, the way crystals settle and sort themselves by density, the way volatile bubbles begin to form and rise. All of these processes follow elegant physical laws, creating order and pattern even in this realm of molten chaos. Our chamber has become a repository not just of molten rock, but of Earth's chemical heritage. Trace elements that tell stories of planetary formation, isotopic signatures that record billions of years of geological history, rare Earth elements that will eventually become concentrated in specific minerals. All of these scientific treasures are being sorted, concentrated, and prepared for their eventual journey to the surface, where human curiosity will one day decode their secrets. The chamber walls continue their slow dance with the magma they contain. Where the liquid touches solid rock, complex reactions occur. Some minerals dissolve while others precipitate, creating reaction zones that record the chemical communication between magma and country rock. These zones will eventually become some of the most interesting features for geologists to study, preserving in solid form the evidence of processes that occurred over thousands of years. As you prepare for peaceful sleep tonight, our underground reservoir continues its patient evolution. The circulation currents maintain their endless dance. The crystallization process continues its slow selection of minerals, and the volatile compounds continue their gradual concentration in the melt. Each night brings subtle changes, each year brings measurable evolution, and each millennium brings our magma closer to the conditions that will eventually drive it toward the surface world. Tomorrow night we'll explore what happens as pressure begins to build in our chamber, as gas bubbles start to form, and as our patient magma begins to sense the pathways that will carry it on the next stage of its remarkable journey. But for now, rest well, knowing that far below, in hidden chambers scattered throughout our planet, the Earth continues its slow but magnificent work of creation, preparing the molten materials that will eventually reshape the landscape above and remind us of the incredible forces that make our planet so dynamically alive. Rising pressure. As twilight settles peacefully outside your window tonight, our magma chamber far below has entered a new phase of its existence. A period of mounting tension and growing potential that will eventually culminate in its dramatic ascent to the surface world. The patient evolution we explored in previous nights has brought our underground reservoir to a critical threshold, where the gentle processes of cooling and crystallization give way to the more dynamic forces of pressure, buildup, and pathway formation. Rest comfortably as we descend once more to our hidden chamber, now mature after tens of thousands of years of chemical evolution. The magma that once flowed so placidly in gentle circulation currents has begun to change in character. As volatile compounds, water vapor, carbon dioxide, and sulfur gases have concentrated in the melt through ongoing crystallization, our magma has become increasingly gas-rich. Like a champagne that has been aging under pressure, building toward an inevitable release. The physics of this transformation are both elegant and powerful. Deep in the chamber, under the immense pressure of miles of overlying rock, these volatile compounds remain dissolved in the magma like sugar in hot water. But as conditions change, as temperatures fluctuate, or as fresh magma arrives from below, the delicate balance between dissolved gases and the pressure holding them in solution begins to shift. This is where our journey takes on new urgency, though still measured in the patient timescales of geological processes. Tonight, as you settle into peaceful rest, imagine the first tiny bubbles beginning to form in our magma. These are not the chaotic bubbles of boiling water, but rather the ordered nucleation of gas phases as the magma approaches volatile saturation. Each bubble represents a small victory of internal pressure over external confinement, a microscopic rebellion against the crushing weight of the overlying crust. These bubbles start smaller than pinheads, forming preferentially around crystal surfaces and chamber walls where the physical structure provides nucleation sites. The formation of these initial bubbles marks the beginning of a profound transformation in our magma's watch. Dissolved gases becomes a complex two-phase system, liquid magma and gas bubbles existing in dynamic equilibrium. As more bubbles form and grow, they begin to rise through the denser liquid magma, creating vertical streams of ascending gas that will eventually accumulate beneath the chamber's roof. This process of volatile exsolution, as geologists call it, is perhaps one of nature's most patient preparations for dramatic change. Each bubble that forms reduces the overall density of our magma slightly, increasing its buoyancy and its desire to rise toward the surface. More importantly, as bubbles accumulate and coalesce, they begin to create a foam-like mixture with properties entirely different from the original liquid magma. As the evening deepens around you, consider the remarkable changes occurring in the physical structure of our chamber roof. The accumulated stress from thousands of years of thermal expansion and contraction, combined with the increasing buoyant pressure of gas-rich magma below, has begun to create networks of microscopic fractures in the overlying rock. These fractures start as tiny fissures, invisible to the naked eye, but they represent the first tentative pathways that our magma may eventually follow toward the surface. The development of these fracture networks follows the elegant principles of rock mechanics. The chamber roof experiences what geologists call tensile stress, forces that try to pull the rock apart. When the strength of the rock is exceeded by the combination of thermal stress, pressure from below, and the natural weakness created by heating and cooling cycles, cracks begin to propagate upward through the crust. This process unfolds over decades or centuries, each fracture growing incrementally, each extension bringing our magma slightly closer to its eventual escape route. But fracture formation is not a simple process of random cracking. Instead, it follows the path of least resistance, seeking out zones of weakness in the overlying rock. Ancient fault systems, contacts between different rock types, or regions previously weakened by earlier episodes of magmatic activity, all become preferential pathways for ascending fractures. In this way, our Earth's geological history influences the routes that future volcanic activity will follow. The chemistry of our magma continues to evolve during this critical period. As volatile bubbles form and rise, they carry with them trace elements and compounds that become concentrated in the upper portions of the chamber. This creates a vertical zonation within the magma body. Gas-rich, highly evolved magma near the top, and denser, more primitive magma in the deeper portions. This stratification will have profound effects on the character of any future eruption, determining whether it will be gentle and effusive or explosive and dramatic. Tonight, as gentle sounds of evening surround you, our magma chamber pulses with a slow but increasingly urgent rhythm. Fresh magma continues to arrive from the depths below, adding both heat and volume to the system. Each injection of new material disturbs the delicate equilibrium that has been building for millennia, causing renewed gas exsolution and adding to the pressure beneath the chamber roof. These recharge events, as they're known, often trigger the final phases of pre-eruption activity. The temperature gradients within our chamber have also begun to change. Where once the system maintained relatively stable thermal conditions, the increasing gas content and the arrival of fresh, hot magma from below create new patterns of heat distribution. These thermal changes affect the viscosity of the magma, its resistance to flow, with gas-rich portions becoming less dense and more mobile, while crystal-rich regions become more sluggish and resistant to movement. As pressure continues to build, the chamber itself may begin to change shape. The intense internal pressure can cause the roof to dome upwards slightly, creating measurable deformation at the Earth's surface that sensitive instruments can detect. This ground deformation is often one of the first signs that a volcanic system is awakening from its long slumber, though the process may still unfold over years or decades before reaching a critical threshold. The volatile compounds accumulating in our magma are not merely passive passengers in this process. They are active agents of change. Water vapor, in particular, dramatically affects the physical properties of magma, lowering its melting temperature and reducing its viscosity. Carbon dioxide creates bubbles that can expand dramatically as pressure decreases, while sulfur compounds will eventually contribute to the atmospheric impact of any future eruption. Deep beneath your peaceful evening, our magma has begun to probe the fracture networks developing above it. Fingers of molten rock, driven by gas pressure and buoyancy, begin to explore the microscopic pathways that have formed in the chamber roof. Most of these early intrusions travel only short distances before cooling and solidifying, but each attempt leaves behind a solidified dike that weakens the overlying rock and creates potential pathways for future magma movement. This process of dike formation represents our magma's first tentative reach toward the surface world. These blade-like intrusions of solidified magma, often only a few feet wide but extending for considerable distances, create a network of potential conduits that will influence all future activity. Some dikes will remain forever frozen in the crust, providing evidence of ancient volcanic processes long after the parent chamber has cooled. Others will become the highways that guide our magma on its final journey to the surface. The interaction between our rising magma and the groundwater systems in the overlying crust adds another layer of complexity to the developing situation. As hot magma intrudes into water-bearing rocks, it creates steam that can dramatically increase pressure in the system. This interaction between magma and groundwater can accelerate the fracturing process, while also creating the potential for explosive steam-driven eruptions, known as phreatomagmatic explosions. As you prepare for restful sleep tonight, our magma chamber stands poised at a critical threshold. The patient processes of chemical evolution have created a system rich in volatile compounds and primed for ascent. The mechanical processes of fracture formation have begun to create pathways toward the surface. The thermal processes of heating and recharge have built pressure to levels that test the strength of the overlying crust. Each night that passes brings subtle changes to this underground drama. Gas bubbles continue to form and coalesce. Fractures extend incrementally upward, and fresh magma continues to arrive from the depths. The system approaches what geologists call volatile saturation, the point at which the dissolved gases can no longer remain in solution under the existing pressure conditions. Tomorrow night, we'll witness the culmination of these building pressures as our magma finally finds its pathway to freedom, breaking through the barriers that have contained it for millennia, and beginning its rapid ascent to the surface world. But tonight, rest peacefully knowing that far below, the Earth is engaged in one of its most fundamental processes, the patient preparation of forces that will eventually reshape the landscape above and remind us of the incredible creative power that lies sleeping beneath our feet. The stage is set, the pressure is building, and our magma waits with geological patience for the moment when the balance will tip and the long journey toward the surface will finally begin. Breaking free. Tonight, as you settle into the gentle embrace of evening, our magma has reached the moment that all the previous millennia of patient preparation have been building toward. The pressure that has been mounting slowly in our underground chamber has finally exceeded the strength of the overlying rock, and our molten traveler is about to begin its most dramatic transformation yet, the breakthrough to the surface world, where it will experience daylight for the first time in millions of years. As you breathe deeply and let the tranquility of nightfall wash over you, imagine the critical moment when our magma finds its pathway to freedom. This breakthrough doesn't happen as a sudden, chaotic explosion, but rather as the elegant culmination of physical processes that have been building momentum over decades or centuries. Like water finding its way through limestone, our pressurized magma seeks out the network of fractures that have been slowly developing in the chamber roof, following the path of least resistance toward the distant surface. The ascent begins almost gently, with tendrils of gas-rich magma probing upward through the fracture network that has been prepared over countless years. These initial intrusions, called dikes, are blade-like sheets of molten rock that slice through the crust along planes of weakness. As our magma enters these narrow conduits, it experiences a profound change in pressure that triggers the rapid expansion of dissolved gases, the same principle that makes champagne foam when the cork is removed, but on a geological scale. Picture this ascent as our magma rises through miles of solid rock, following pathways that may be only a few feet wide, but extend upward like underground rivers of molten stone. The journey from chamber to surface might take hours, days, or weeks, depending on the magma's composition and the complex plumbing system it encounters. Gas-rich, less viscous magmas can rise relatively quickly, while thick, crystal-rich magmas move more slowly, sometimes stopping and starting as they navigate the mechanical challenges of their ascent. As the magma rises and pressure decreases, the dissolved gases come out of solution with increasing vigor, creating a foam that can expand to many times the original volume of the liquid magma. This process, called the circulation, transforms our once dense molten rock into a lighter, more buoyant mixture that rises with increasing speed toward the surface. The bubbles themselves become agents of change, their expansion creating additional pressure that helps to widen the conduits and accelerate the ascent. Tonight, as peaceful stillness settles around you, our rising magma encounters its first major decision point. The style of eruption that will occur depends largely on the gas content of the magma and the ability of those gases to escape. If the magma is relatively gas-poor, or if the conduits are wide enough to allow gases to escape easily, our volcanic awakening will be gentle and effusive, a beautiful outpouring of molten rock that builds new land with patient persistence. In this effusive scenario, our magma emerges at the surface as lava, flowing like a river of liquid stone but moving with the measured pace of cooling rock. The temperature at eruption might reach 2,100 degrees Fahrenheit, hot enough to melt copper, yet the lava flows move slowly enough that they rarely pose immediate danger to life. These flows represent Earth's most direct creative process, the literal manufacturing of new land as molten rock cools and solidifies in contact with air and water. But if our magma is rich in volatile compounds, and if the conduit is narrow enough to restrict gas escape, the eruption becomes more dramatic and explosive. In this scenario, the rapid expansion of gases fragments the magma into countless tiny droplets and crystals, creating the spectacular displays of volcanic activity that capture human imagination. These pyroclastic eruptions launch material high into the atmosphere, creating towering columns of ash and gas that can reach the stratosphere. The physics of explosive eruptions are both beautiful and complex. As gas-rich magma reaches the surface, the sudden drop in pressure causes the dissolved volatiles to expand so rapidly that they shatter the surrounding liquid rock into fragments ranging from fine ash to large volcanic bombs. This fragmentation process, called explosive decompression, can accelerate these fragments to velocities exceeding the speed of sound, creating the rushing sounds and shock waves associated with volcanic explosions. As you rest comfortably this evening, consider how our magma's long journey through the crust affects its final character at eruption. During the ascent, continued cooling causes additional crystallization, while the loss of gases changes the magma's density and flow properties. Magma that began its journey as a simple basaltic melt might reach the surface as a more evolved andesite, while highly evolved rhyolitic magmas might become so gas-charged during ascent that they produce the most explosive eruptions on Earth. The breakthrough to the surface represents more than just a physical transition. It's a fundamental change in environment that transforms our molten rock in multiple ways. For the first time in millions of years, our magma encounters oxygen, leading to oxidation reactions that change both the chemistry and color of the erupting material. The interaction with atmospheric water vapor creates new chemical compounds, while the dramatic temperature contrast with surface conditions accelerates cooling and crystallization. Different types of volcanic landforms emerge depending on the character of our magma's surface debut. Hawaiian-style eruptions, characterized by fluid basaltic lavas and relatively gentle gas release, build broad shield volcanoes with slopes as gentle as those of medieval shields. Stromboli eruptions feature more vigorous gas release, but still produce mainly lava flows, creating the classic cone-shaped volcanoes with steeper slopes, built up by alternating layers of lava and pyroclastic material. More explosive eruptions create different landforms entirely. Vulcanian eruptions, named after Volcano in Italy, produce short-lived but violent explosions that create steep-sided cones built primarily of volcanic fragments. Plinian eruptions, the most explosive type, create towering eruption columns that can inject material into the stratosphere. The physics of explosive eruptions are both beautiful and complex. As gas-rich magma reaches the surface, the sudden drop in pressure causes the dissolved volatiles to expand so rapidly that they shatter the surrounding liquid rock into fragments ranging from fine ash to large volcanic bombs. This fragmentation process, called explosive decompression, can accelerate these fragments to velocities exceeding the speed of sound, creating the rushing sounds and shock waves associated with volcanic explosions. As you rest comfortably this evening, consider how our magma's long journey through the crust affects its final character at eruption. During the ascent, continued cooling causes additional crystallization, while the loss of gases changes the magma's density and flow properties. Magma that began its journey as a simple basaltic melt might reach the surface as a more evolved andesite, while highly evolved rhyolitic magmas might become so gas-charged during ascent that they produce the most explosive eruptions on Earth. The breakthrough to the surface represents more than just a physical transition. It's a fundamental change in environment that transforms our molten rock in multiple ways. For the first time in millions of years, our magma encounters oxygen, leading to oxidation reactions that change both the chemistry and color of the erupting material. The interaction with atmospheric water vapor creates new chemical compounds, while the dramatic temperature contrast with surface conditions accelerates cooling and crystallization. Different types of volcanic landforms emerge depending on the character of our magma's surface debut. Hawaiian-style eruptions, characterized by fluid basaltic lavas and relatively gentle gas release, build broad shield volcanoes with slopes as gentle as those of medieval shields. Strombolian eruptions feature more vigorous gas release, but still produce mainly lava flows, creating the classic cone-shaped volcanoes with steeper slopes built up by alternating layers of lava and pyroclastic material. Tonight, as gentle night sounds provide a peaceful backdrop to your rest, our erupting magma begins its interaction with the surface environment in ways that will influence the local ecosystem for generations to come. Volcanic eruptions are among nature's most powerful agents of landscape change, capable of burying existing topography under layers of new rock, damming rivers to create lakes, and building mountains where none existed before. The gases released during eruption, water vapor, carbon dioxide, and dozens of trace compounds, become part of Earth's atmospheric system. While large eruptions can temporarily affect global climate by reflecting sunlight with their ash and aerosol clouds, the long-term effects of volcanic activity are generally beneficial to life on Earth. Volcanic soils are among the most fertile on the planet, enriched with nutrients released from the breakdown of volcanic rock. The cooling process begins immediately as our magma contacts the surface environment. Lava flows develop a skin of solidified rock while remaining molten internally, creating natural insulation that allows the flows that travel considerable distances before completely solidifying. This cooling creates different textures and rock types depending on the rate of heat loss. Smooth, ropy pahoehoe lavas form when cooling is gradual, while jagged lavas result from more rapid cooling and higher gas content. As our magma continues its surface journey, it begins to form the igneous rocks that will become permanent additions to Earth's crust. The rate of cooling determines the final texture of these rocks. Rapid cooling creates fine-grained or glassy textures, while slower cooling allows larger crystals to form. These textural differences tell the story of our magma's final moments, preserving in stone the conditions that existed during those crucial hours or days of surface cooling. The volcanic gases that accompany eruption carry with them chemical signatures that reflect the deep earth source of our magma. Scientists can analyze these gases to understand the conditions in the mantle source region, the processes that occurred in the magma chamber, and the changes that took place during ascent. In this way, our erupting magma becomes a messenger from the deep earth, carrying information about realms that humans can never directly explore. Tomorrow night, we'll follow our magma as it flows across the surface world as lava, building new landscapes and beginning its transformation into solid rock. But tonight, rest peacefully, knowing that somewhere on our planet, magma that began its journey in the deep mantle is breaking through to the surface, beginning the final chapter of its epic transformation from the hidden depths to the open sky. The breakthrough has occurred, the ascent is complete, and our magma now faces the surface world for the first time in geological ages. The patient forces that built pressure over millennia have achieved their purpose, and the creative power of Earth's interior is about to reshape the landscape above in ways both dramatic and beautiful.